All right, here we go. Here, here we go. Here we go. Here we go. All right. So, if you have a moving charged particle, ooh. Oh my God! Remember Run, that game? Here we go. Here we go. Here we go. That's That's the magnetic field produced by a moving charged particle. Obeys the right hand rule. Yep. This is V Python. Okay. Is everybody good with that? Foundational fact number one: moving charged particles create a magnetic field. This is demonstrating that. Yep. Okay. Okay. So.
How is that second word pronounced?
Bizarre. Leo Bizarre. So Biot-Savart. It's someone's last name.
Whose last name? Oh, Leo. Wait, is that actually a person? Right.
Why can't they just write it in IPA?
It's like Gauss's law. It's just
You're taking the test on 26?
Yeah. I can't.
Okay.
It's in there. Did you not see it?
Oh, it's in there. Can we pause class?
Everyone did that on it, even with test credit.
What?
But I'm not in chem, so whatever.
No, it's easy.
No, I had a whole like the class average was like 100%.
I did good, everyone.
No. You're the outlier. You don't count as the average.
That was my least studied for test. I was worried about it.
Get on it.
All right. So here we go. Here we go. Here's how we interpret this equation, because I'm assuming you just wrote that down like whatever. Yeah. Okay. So what we've got is it's a cross product, so we're looking at the component that's perpendicular. Okay. So here is, I'm going to orientate my axis along the radius vector and then go perpendicular to that. Okay. I want the component of velocity. So velocity is doing this. I want the component of velocity that is perpendicular to this axis. So I want this component here. That's V perpendicular to this radius vector. Does that make sense? They're multiplying those two quantities, this radius. Actually, this is the unit vector, so it has a magnitude of 1 by this, and then so this is your V sine theta. This is your V perpendicular. Okay, and then because it's a cross product, you have to do the right hand rule. It's orthogonal to this plane of the radius and the velocity vector. So it's coming out three-dimensionally. Like here's the plane, it's coming out like that. Okay, and that's the magnetic field that's created. Okay, by a single charged particle. Okay.
How do you use the right hand rule for this?
So you stick your thumb in the direction of velocity, and it curls around. This is right hand rule number 1. Okay. Yep. Because what we're going to go to is a wire with current going through it. So it creates its own magnetic field. And so right at this location, It gets stronger. Yep. Good with that. The angle that they're referring to, theta here, is the angle between the velocity vector and that radius, the vector. Okay. Good with that? Okay. So Tesla is the SI unit. That's pretty strong unit for, like, it's a big unit. One Tesla is a big magnetic field. So surface of the Earth, 5 times 10 to the negative fifth. Refrigerator magnet, 5. So this is like 100 times stronger. Someone was asking how strong is Earth's magnetic field? 100 times weaker than a refrigerator magnet. Okay. Like a MRI, I want to say is around 1-2 Tesla, somewhere in there. So it's like get rid of all ferromagnetic materials. And like if you ever had like a metal plate in your head, that would not go well. Pacemakers, bad. Like, okay, so watch this. This is a permeability constant. This is permittivity constant. I've never seen anybody test over that, but just know that they're not the same thing. But they look like the words look similar. Both start with a perm. Okay.
I got the freaking units wrong. I put m over a squared.
Yeah. Bummer. Okay. So you could just plug in that for your permittivity constant. All right. So here's another animation of yep. Okay. Good with that? So as it gets closer to the radius, so that's your radius vector. Okay.
Yeah, get out of here.
Bringing the presents you like eating the pack. That's most of the pack is doing today. That's not how presidents moves. The president hangs back and does nothing.
Yeah, they're making a caravan for him. So if anyone was gonna shoot a car, they would. Yeah. Majority of us. Oh, there was a question on this.
There was.
Brain expanding.
Brain expanding makes it sound
That's what happens if you have something in your head.
That's why we made an MRI.
Am I missing something?
Velocity.
Oh, velocity's into the screen. I was like, the answer is 0. There's no motion.
It's just positive.
Got it. Okay, correct. Yeah, I was like, there's no magnetic field. That was a trick question. Does everybody go with up?
Yeah.
Okay.
Smiley. After the AP test, can we mess around with MRIs?
that sounds like a good way to get arrested.
We perform brain surgery. Put a magnet in there and stick them in an MRI.
Feel
like a human watching this.
First, if you want to really harm someone's magnets, just have them ingest one.
That is true. Yeah. Oh yeah, you can just eat one and we wouldn't have to learn brain surgery.
We would have to learn.
All right, here we go.
Oh, that's positive and not that it's going into the page.
It's going to the right.
Interface with apps.
Oh boy.
Oh yeah.
Oh, we just saw this one. Except we didn't.
Go your neighbor.
D.
How?
D.
I didn't get that.
Okay, well, first of all,
Right hand rule.
Oh, it's not.
first of all, you do right hand rule doesn't make sense. And second of all, there's no component of velocity that's perpendicular to the radius.
That's
Okay, there we go with that. 0.
Yeah.
No component of velocity is perpendicular to
Okay, so it's
the
not a trick
radius.
question.
Not a trick question. All right.
It was for me.
No, I was no. The trick would be it's not entirely perpendicular.
Oh, it's like off right. So the thing is like that. Oh,
Ooh, this is not actually that complicated.
That's weird, actually.
Mhm.
Okay, so
Well, yeah, but
there's
they're
both positive.
You got an electric force that
Field
does not
that's
that.
right. If I put this phone on the other side of my I think it's 2 wires. If we do it like this,
Then it works.
Okay. This is the same question as 2 wires that have current going the same direction. Okay. So, direction magnetic field in the upper. So this one, the lower one creates a magnetic field coming out of the page. Out of the page, thumb goes to the right and forced down. Daniel.
Stupid question. Would they also repel?
They would. So then the follow-up question, does everybody catch that? Like the magnetic forces pushing them together.
That's why the sun has a stupid magnetic field. What? It's a bunch of charged particles
moving.
moving around
Yeah.
crazy fast.
Yeah.
That makes sense.
Yeah.
Okay.
Which do you think's stronger? The electric force of repulsion or the magnetic force, we'll say, of attraction?
Everyone was wrong.
magnetic.
I don't know the answer to this. Like I'm kind of throwing that out there. Like
I would assume
Think about this.
So this one they go together.
they go together. They're being forced down.
It should depend. It should depend on it should depend on the velocity. On the velocity, so that would determine the strength, because that would modify the strength of the field.
Wait, why is it
Just like 2 wires with current. So this guy created a magnetic field going out of the page.
Yeah.
This one's in that magnetic field
Yeah.
being forced down. Right.
It doesn't matter. It doesn't matter.
You're right.
Same concept.
Goes down.
Yeah.
So wouldn't it be forced that way?
No, the magnetic field's going that way. Is into the page. But the force is your palm.
Oh, because.
You do first right hand rule, and then you do second right hand rule. Okay.
The strength of
I would say actually the magnetic force. I'm going to say this based off of just experience. I've done this with the wires before, and they end up attracting.
I knew it.
So you're saying the magnetic field.
Okay, but also.
But in a wire magnetic field net neutral.
What?
I know.
But isn't a wire net neutral?
No, not if it's direct current.
Not if it's direct. Oh, really?
Yeah, if I'm alternating current, yes, direct current now.
I didn't know that.
So like here, yeah, there it is. This times 10 to the -7, -12.
So if it asks something like that, would it say like ignore the electric charge?
Except it's not even to the -7. It's actually 10 to the -6. So yeah.
Correct. Yeah, you would ignore the electric force. All right. So that's a particle. So this is what this was at the very foundation. Okay, like you want to like look at foundational. I didn't introduce this to you last year because it wasn't really necessary. But we start. This is like smallest particle, and then we bring it up to something more applicable, which is wire.
Oh,
Okay, current with wire in it. So they're building this idea with you have a certain amount of charge that has a certain velocity, and so that velocity is how far it traveled in a certain amount of time, and then we're going to use that time. So this is current multiplied by the distance it travels. Okay, so that and so during this very short segment current, this is what you get on the equation sheet. Okay, this is what you read out of the book. Okay, so the change in length is your delta S, and I would not use this. Well, I mean, you could. This is helpful for computer programming. Like if you're putting that in VPython, your computer can talk this way. Okay, but I would use this and just use your right hand rule. Okay, Daniel.
What's the difference between the sine glass and the DS? Because why is it causing an arcs?
Good question. That's not causing it. So the DS, we're just getting small, really small of this. The difference between this equation and this is the unit vector, and this is the actual vector. So this has magnitude, and so to cancel that out, we need to cube that to negate because the unit vector is just your vector over the magnitude of that vector.
And R happens to be the magnitude of that vector for other reasons.
Yep. Okay. So this is how you'll see that. This is what I would do. I would apply this, like use this way. So know that just this is sine theta times ds.
In this instance, what's theta? Is it
Great question. It's always the angle, and yeah, this is why I'm not a huge fan of this, but all texts do it. It's the angle between the current and the radius, what you're trying to evaluate. Technically, if I was writing physics, I would do the perpendicular component of current. Okay. Good with that? Tell your neighbor. Agreed. Everybody good with the
current
okay?
No.
I remember the equations.
Yes.
Tell your neighbor.
Oh, because that's when you sign. Yeah.
Yeah, your sine.
Okay. Everybody good with that? C. Okay. The opposite over hypotenuse is sine. Okay.
Because you got it. I'm gonna be really mean to you for a second. No, I'm not good. To the record. Yeah. City, it's almost the Calvin City.
Oh wait, I think.
You're just gonna pump him into his head. Oh, you suck. Oh, I went down, bro.
How do you do this?
I think I know how to do it. It's just
I'm gonna pick one
I'm
up.
just trying to educate.
We're gonna do that.
Gauss's
No, that one. No doubt. Frick.
Okay.
It's gotta be.
So here,
It has to be airs. It has.
oh, there we go.
That's the limits.
That's the reason.
Wait, were we just on different sides?
yeah, we're building up to this.
These.
I should. Let me do this.
Oh. No Nintendo.
Let me do this.
We have the 3 halves hour.
And you said yo, which means I. Well, yes.
Wait, it was not there. I'm just gonna write down the one that I
Sam.
Sam, take notes. Sam, do this question. Let's see.
They always are just for me.
They always want me to do business.
Understand.
Okay, tell your neighbor.
2. 1 or 2.
Daniel,
how can it be 2 though?
Yeah.
Oh, it is 2.
Yeah.
Oh, it is 1.
Actually, one, you need our.
How do you do this?
No, it's 2.
Or like.
R is the
yeah,
little r is the square root of x squared plus r, big R squared, because of Pythagorean
Oh yeah.
or the theorem of Pythagoras.
Right.
It's what linear algebra calls it.
Okay.
Our linear algebra, we can't figure out why it's.
Is everybody good with 1?
Yeah.
Okay, so this R is equal to the square root of x squared plus r squared. Okay, so that's just x squared, r squared, 1/2 times and that's cubed. So r cubed. There we go with that. And then the I and the r come out. There we go with that.
Yes.
Okay. So if we integrate this, we end up with this. Okay. We don't need to, because we're going to use Ampere's law to do the shortcut. Ampere's law to get this is super crazy easy. We could go through all the calculus like I made you do with static electricity. Not necessary. You've already gone through that. Okay.
Isaac, I didn't know how to do it.
You'll be able, just like a point charge, you could drive the electric field like that with Gauss's law. You'll be able to drive the magnetic field like that with Ampere's law, with a straight wire.
Wait, Ampere was a guy?
He was.
Just like Faraday.
And Newton.
And Gauss.
And Gauss.
And
Yeah. No, if I would make it a unit for momentum. because that doesn't have that.
Can we call you English?
That wouldn't fly beyond this classroom. Like he doesn't even have his PhD.
Neither did Nathan.
This is true, but
I'm gonna start calling it.
I hope you were calling it that before.
all right, here we go.
Yeah. No. No.
Hold on, I gotta read the question.
Oh, kilograms meters per second squared. Wait, no. Shoot, it's cubed. No, it's not cubed.
There.
I'm doing kilograms meters per second.
Oh, shoot. I already forgot the equation.
Well, but prepare to be
I'm
wrong.
showing you the equation.
Oh, Newton seconds. That's where that comes from.
You're going on a train right now.
I'm being smart right now. I just don't understand.
No one is being smart right now.
Okay.
Not even me.
It gotta be B. It's gotta be B. It's absolutely
I
B.
said what I said.
Gotta be B.
Correct answer is
You gotta be B.
Gotta be
B.
All the other ones, they're
Okay. All right. So here, this you need to actually know how to do. No. No. Okay.
Especially how slow he is.
So
Filibuster time, guys. Go, go, go.
we are taking a little. We're taking a little segment. I want to get through this Biot-Savart, and then we can do Ampere's law tomorrow. That's what I'm going for. Okay.
Let's go.
All right. So, how would you set this up?
Bottom bound.
I put the top part in the integral.
I would put the right top
Take
part.
out the I.
Yeah, that's what I'm
Take
talking
out all the
about.
constants.
And then I would go 0 to 2 pi.
I would get two.
Wait,
I would
no,
get two.
I would go 0 to 2 pi r because it's DL.
I would go 0 to 2 pi r.
I agree.
Yeah.
Wait, what?
And then
It's
Just integrate.
But what's special about the circle?
There's
yeah.
nothing special.
It's a-
about it.
Special about the
It's
circle
normal
is
like
that you can use
everyone else.
0 to 2 pi to get like the little break. So you can get circle.
Oh, over there. Oh wait, no, you could use it.
Yeah, you just plug that in and then you
No, I
put
thought
the
it was like
things
find the current. Like, no, like going to Z direction. You look at that current's being given.
in. Okay, yeah, I got you.
Yeah.
So much quieter with clothing time.
Yeah, but why would there be an R? Why is there an R?
Why not?
Okay.
So this is perpendicular. This goes to 1 because your theta is here's your current and here's your R. It's perpendicular. So theta is equal to 90. Okay. So
I mean, yeah, you can have bigger or smaller loops. That's fair.
okay. Go to that.
why decide on one?
Because the direction of current
Yeah, from the center.
is going this way, and then compared to where we're trying to observe, this is R, and then this is I. So they're perpendicular at the center. Over out here, it's not perpendicular.
What's perpendicular to what?
The current direction, or DL, a little chunk, is perpendicular to our radius vector. Those are perpendicular. Okay. So we're integrating that. So we're adding 1. So you get -2 R to the negative first, and then we're going 2 pi R, 0. Oh, ugly. Uh-oh. Uh-oh. 0 something. Oh. What?
Is is L the same as R?
Yeah, it's a length.
Yeah, and so that's L. So you could rewrite it as L to the negative.
No,
No, so this is constant.
Yeah, that big R is constant, or little r.
Oh yeah. Sorry.
I'm just confused why we're integrating with respect to dl and then r.
Oh, that was a great question.
We don't need
R should stay constant. So R squared, because R is. So we get 2 pi R. That cancels out, and we get that expression there.
But if it's not at the center, it's not.
Yeah, well, no, if it's at the center, then it
Right.
still works because Ampere's law.
Right.
It's just Gauss's law, right? That's how that works.
So no, not for a. This is the one thing you have to do.
Oh, Dad, I got that place right. So if I go somewhere different than the loop,
Yes, sir. Yes, sir.
I don't want to do that.
Yeah.
That's what I had.
I had one for a loop and then one for coil, and I'm like, oh shit. I thought we put the coil down for solar. Like, you want to go pass out the comment?
Yeah, sure.
Okay.